Okay, so welcome back to this next video in which we are discussing subgroups. Okay, so we've discussed that a subgroup capital H of the larger group capital G is first and foremost a subset of capital G. Okay, so it's a subcollection of the symbols that you had in capital G basically. Okay, so here is this subset shown here in blue. Okay, now for any subset you can dream up of capital G, you can build a very easy composition law on that subset. Okay, you can just steal the composition that you had from capital G basically. Okay, so if you want to know what x composed with y is, where little x and little y are elements of our subset capital H, then quite simply all you can do, what you can do is just go back to the composition law on capital G here and say, okay, little x and little y were both elements of capital G, okay, so I can compose them together in capital G and get the answer little x composed with little y, and I'll just take that answer and stick it into my composition table that I'm building here. Okay, so basically my composition table that I'm constructing here will just be the restricted composition table here, so you'll just take out all of the elements of G that are not in H basically from this composition table, and what's left you'll use as your composition table on big H. So you're just restricting the composition table down to elements of big H basically, so that it covers all possible compositions of elements of big H. Okay, right. Now you can do that for whatever subset you like. Nothing that I've said there is specific for certain subsets. You can do that for absolutely any subset of big G. However, only for certain special subsets is this going to be a subgroup. Okay, in order for this subset with this inherited composition law on it to be considered a subgroup of capital G, written capital H is less than capital G and read as capital H is a subgroup of capital G, this is only a subgroup when this is actually a group in its own right. So forget capital G and forget its composition law, just look at this and ask, is this actually a group? Okay, and if it is a group, then we call it a subgroup of capital G. Now what does that mean? It means that the composition law here needs to obey all of the axioms of group theory, and we were just going through these axioms of group theory when we finished the previous video. Okay, right, so let's continue that on. So we'll just go over the ones that we'd already discussed. So firstly, it needs to obey closure. Now that suddenly becomes non-trivial in the concept of subgroups, okay, because there is a very real risk that when you compose two elements of capital H together, that you will end up with an answer that is outside of capital H, okay, because what we know is that when you compose little x and little y together in our composition law on big G, that it will give you an element back in big G basically. That's assured because big G was a group, but we are not assured at all that when we compose any two elements of big H together that we will necessarily get an element of big H back again, and not some element that's in big G but not in big H. So closure suddenly becomes very, very important when we're talking about subgroups. Okay, now, as I was saying at the end of the previous video, associativity, which is usually the most complicated of the axioms of group theory, suddenly becomes trivial in the concept of subgroups, okay? Because we inherit associativity from the composition law of our larger group, capital G here. Okay, quite simply, if we have three elements, let's say little a, little b, and little c, which are all elements of capital H, so let's say all three of these are representing elements of our subset, capital H here, and let's suppose that this composition of the three of them didn't obey associativity. Okay, so it wasn't the case that it doesn't matter where you put the brackets, okay? So it was the case that A composed with B and then composed with C was not equal to A composed with the answer to B composed with C. Okay, so let's say we could find a place where associativity does not hold for our composition law here on big H. then that would imply that this was also not holding in big G, because if A, B, and C are all elements of big H, then they are certainly elements of big G, because big H is just a subset of big G. So that would mean that this composition was valid in big G as well, and therefore big G wouldn't obey associativity if big H didn't obey associativity. So basically you can prove that if big H doesn't obey associativity, then it implies that big G doesn't obey associativity, and since we're assuming that big G is a group, it must obey associativity, and therefore we've proven that big H cannot possibly not obey associativity, since the composition law is effectively just the stolen composition law from capital G, basically. So associativity becomes the trivial property, basically. Okay, next up, the identity. So we need now an element in big H which will compose with all other elements in big H on either side to give those other elements of big H back again. Okay, so really this just amounts to saying that we need the identity element from big G to be present within big H. So one of the elements that you have to include in your subset is the identity element from big G. So you must include whatever the identity element was in big G in big H, basically. Okay, that's the only way that you're going to get an identity element in big H. Okay, finally, we need inverses. Okay, so we need it to be the case that for any elements that you have in big H, okay, so I'll just write this out, for all, let's say, little h is an element of big H, so for all elements in big H, basically, we need it to be the case that you can find another element which isn't necessarily distinct. There must exist another element which we'll call H inverse, which is also in big H, so there must be another element in big H such that when we compose them together, either way round, it gives us the identity back again. So H composed with H inverse is the identity, and H inverse composed with H is also the identity. And I've just dropped the composition symbol there and just written them next to each other to demonstrate composition. Okay, so this needs to be true. You need to be able to find elements that are inverses for an arbitrary element, basically. So we need our composition to be closed under inverses, basically. For any element, we need to be able to find another element which we can compose with that element to give back the identity. Okay, so thinking in terms of the elements, once again, as representing set permutations, what this says is that you need to have if you have any set permutation represented by a symbol included in big H, our subset here, you need to also have another symbol which is representing the inverse set permutation, basically, also included in big H, basically. Okay, right, so that now is the definition then of a subgroup complete. What I now want to do is illustrate this concept by doing some examples with groups that we have seen before. So we're going to look at subgroups of the symmetric group on free elements, and we're also going to look at subgroups of the group of integers under addition. However, before we do that, let me just talk about two subsets of any arbitrary group that are always subgroups, because there are two trivial subgroups, as they're called, which are absolutely always subgroups. Okay, so before we go on to discuss some more interesting examples, let me just talk about, for an arbitrary group, the two trivial subgroups. Okay, so for any group you can easily find two subgroups, and these are called the trivial subgroups. Okay, right. So one of the trivial subgroups is the entire group itself, and I alluded to the fact that this was going to come up earlier on when I talked about the fact that actually the set containing all the elements of the group is actually considered a subset of the group. Okay, so strictly by definition, even though it's a bit idiotic to say it, the entire group is a subgroup of itself. Okay, so you can take as your subset, capital H, the entire set of the group, and that is considered a subset, basically, of the group G. Okay, then the composition law you get will just be an exact replica of the composition law here, and since this was a group, then of course our subgroup is going to be a group, because it's just the exact replica of our group. Okay, so one subgroup that you can always find for an arbitrary group is the whole group itself. Okay, so that's a little bit stupid, but it is a subgroup. Okay, right, so that's one of the trivial subgroups. However, there's another one that is slightly more interesting than this one. Okay, the other trivial subgroup is the subgroup where you just have one element in your subset. Okay, so this is going to be the subgroup where the only element you take is the identity element. Okay, and that's it. So all groups have identity elements. If you want to construct a subgroup, a trivial subgroup, for any group you like, all you can do is take the identity element from that group, stick it into a set by itself, and then what's the composition law that you'll get? Okay, well the composition law you'll get is just the identity composed with the identity is the only answer you need, and of course we know what the identity composed with the identity is. For all groups, the identity composed with the identity is just the identity, otherwise the identity wouldn't be an identity element. Okay, and that does obey all the axioms of group theory. Okay, and in fact it is isomorphic to the group of the symmetric group on one element. Okay, so this will be isomorphic to S1. Okay, right, so that is always a subgroup for absolutely every single group. You can always take the identity element, put it in a set by itself, and the composition law will always be like so, and this is the group isomorphic to the symmetric group on one element, which we saw in our videos on the symmetric groups. Okay, right, so those are always two trivial subgroups that you can find for a group, basically. Okay, those are the uninteresting ones, basically. Okay, all other subgroups that are proper subsets and which are not this small, basically, that they only contain the identity element, are called proper subgroups. Okay, so really, when we are studying subgroups of groups, we are more interested in proper subgroups rather than these trivial subgroups. Okay, and when we now go on to our examples, we're really going to be looking at proper subgroups rather than these trivial subgroups. But be aware that for any group you can easily find two subgroups, which are these two trivial ones. Okay, right, so now I've got that bit out of the way, let's now talk about examples, okay? Let's do the example of the symmetric group on three elements, and let's have a look at some subgroups of the symmetric group on three elements. So firstly, let me just remind you of the symmetric group on three elements, okay? So remember, it is denoted S3, okay? And the way that you can think of the symmetric group on three elements is you create the set containing three numbers. Okay, you create the set which contains the three numbers 1, 2, and 3. Okay, and you can think of the symmetric group on three elements as being the group that you create by giving every possible set permutation of the set containing these three numbers a symbol. Okay, and then you define the composition law on that set of symbols, which is representing all possible set permutations of this set of three elements, by composing the set permutations that those symbols represent. Okay, so let's go through this. So I'll just remind you of the structure of this group then. We need to look at all possible set permutations of this set of three elements, basically. Okay, and we need to give all of those set permutations symbols, put those symbols into a set, and that's going to be our S3 group. And then we need to define the composition law. Okay, so let's have a look at all the possible set permutations of this set containing three elements then. Okay, so there is the identity map then, which maps all of these symbols onto themselves. Okay, so I'll map 1 onto 1, 2 onto 2, and 3 onto 3. That is a set permutation of this set of three elements, basically. And we will give that set permutation the symbol I. Okay, and indeed this symbol I is going to be our identity element within the group S3. Okay, right. Next up, let's consider the transposition set permutations. Okay, so there are three transposition set permutations of a set containing three elements. Okay, so you can transpose 1 and 2 around, okay, and keep 3 the same, and we will call that set permutation the transposition of 1 and 2, tau 1, 2. Okay, so this is tau 1, 2. Next, you can transpose 1 and 3 and leave 2 the same. Okay, so I'll draw out this set permutation. So we'll send 2 onto itself and we'll swap around 1 and 3. So 1 will go to where 3 is and 3 will go to where 1 is. We'll call that the transposition of 1 and 3, tau 1, 3. I'll cover that one in turquoise. Okay, and then the final transposition is where we swap 2 and 3 around and leave 1 the same. Okay, so 1 will go to 1 and 2 and 3 will get swapped around like so, and we'll call that the transposition of 2 and 3. Okay, and I'll underline that one in pink. Okay, right, now there are 2 more set permutations for this set of 3 elements, because there are only going to be 6 in total. You can work that out because the size, the total possible number of set permutations has to be 3 factorial. Okay, quite simply because when you think about how many different things you can send 1 onto, there are 3 different things you can send 1 onto. You could send it onto 1, 2, or 3, so that's 3. Then for all the different places you can send 1 onto, you then have 2 choices, 3 minus 1 choices of where you're going to send 2 onto, so that's times it by 2, and then where you send 3 after that is set, because once you've chosen where 1 and 2 go to, 3 has only 1 choice basically. Okay, so it's 3 times 2 times 1, so there are 6 possible permutations. Okay, so we need 2 more basically, and these are the 2 permutations where you move absolutely everything. You can see that the transpositions, you only move 2 elements, you swap 2 elements around. The final 2 permutations are where you move everything. Okay, and these are the cyclic permutations. Okay, so I'll put one of them up here. Okay, so 1 is going to be that we move everything along by 1. So 1 will go to where 2 is, 2 will go to where 3 is, and 3 will go to where 1 is. Okay, and we'll call that set permutation sigma. Okay, and I won't colour it in green, we've already used that, I'll colour it in red. Okay, the final set permutation is the one where you move everything along by 2. So 1 will go to 3, 2 will go to 1, and 3 will go to 2. Okay, and that is effectively just do sigma twice. So we call it sigma squared because it is sigma composed with sigma. Remember, sigma is move everything along by 1, so moving everything along by 2 is equivalent just to doing sigma twice. So 1 will go to 3, 2 will go to 1, and 3 will go to 2, okay? So this is called sigma squared. Okay, and I'll have sigma squared coloured in here in yellow. Okay, so here are all the possible set permutations then of this set containing these 3 numbers. Okay, and we've now given all of these set permutation symbols. So what we're going to do to create the group S3 is we're going to stick all of these symbols together into a set, and this is our set that's going to form a group then. Okay, so we'll have the identity element here, we'll have tau 1, 2, tau 1, 3, tau 2, 3, sigma, and sigma squared. Okay, so here is S3 basically. Okay, right. Now, of course, that's just a set at the moment of symbols. In order to turn it into a group, we need to define a composition law, and the way that we will do that is, where can I draw this? I'll put it down here. Okay, so we'll call the composition abstract composition here. We'll put every symbol up here to give every symbol a column. So we'll have I, tau 1, 2, tau 1, 3, tau 2, 3, sigma and sigma squared. And I don't think it will fit down there, but I'll have a go. I, tau 1, 2, tau 1, 3, tau 2, 3. And I won't be able to fit sigma squared in, but you'd have sigma squared underneath here. Okay, you'd have to extend it a little bit. Okay, and what you'd then do is you'd go through and put in the answers for all 36 of these entries. Basically, you've got 36 things to work out basically. Okay, and the way that you will work out what any 2 of these elements compose together is, so the way you'll work out what little x composed with little y is equal to is you'll think, okay, this symbol little y, okay, and both of these are representing variables, so little x and y could be any one of these symbols basically. Okay, so you'd say the way that I'll work this out is I'll think back to what set permutations do these symbols represent, and what I'll do is I'll do the set permutation represented by y first, and then I'll do the set permutation represented by x after that, okay, and then I'll work out what the net set permutation is, okay, and whatever that net set permutation is, I'll look at what symbol represents that net set permutation, and I'll stick that symbol in as the answer in my composition table. So just to do an example, if we look at tau 1, 2 composed with tau 1, 3, that will mean do tau 1, 3 first and then do tau 1, 2. So what you'll do is like so. You'll do tau 1, 3 here, you'll swap 1 and 3 around and send 2 onto itself, and then you'll do tau 1, 2, so you'll swap 1 and 2 around like so, and you'll keep 3 the same, and you'll work out what is the net result there. Okay, well, I send 1 overall to 3, so I'll write down the net result down here, just for lack of space. Okay, so 1 overall goes to 3. Okay, where does 2 go to? Well, 2 originally goes to 2, but now it goes to 1, so 2 will go to 1, and 3 goes to 1 but then goes to 2, so 3 will go to 2. And we can see that that is sigma squared, so the answer to tau 1, 2 composed with tau 1, 3 is sigma squared basically. So I would stick in here, tau 1, 2 composed with tau 1, 3, I'd stick in sigma squared, and you can do that for all 36 entries. Okay, now that is assured then to be a group, because it's assured to be closed, because when you compose any two elements together, you are assured to get another answer basically, okay, because of the way I've defined this. Whenever you compose two of these set permutations together, you must get another set permutation. All of the set permutations have a symbol representing them, and therefore every single one of these compositions must give another answer within the group basically. So it is closed. It is going to be associative because we're thinking in terms of set permutations, and composition of set permutations is associative basically. It does not matter where you put the brackets basically, because after all, if you compose 3 set permutations together, if you imagine sticking another one after this, okay, that has an answer. Okay, the net set permutation has an answer. It doesn't matter where you put the brackets with regards to composition. It has an answer, one and only one answer. Okay, so that's really why associativity holds whenever we think of the symbols of a group as representing set permutations in this way. We will have an identity element because we have a symbol representing the identity permutation here, and whenever you compose the identity permutation with any other permutation, it'll just give that other permutation back again, and that's true either side that you put the identity. Okay, and inverses, well, we have absolutely all set permutations represented here. Okay, when you look at any set permutation, so let's take sigma as an example here. Okay, the inverse map, which reverses what sigma does, so sigma sends 1 to 2, 2 to 3, and 3 to 1. The inverse map would send 1 to 3, 2 to 1, and 3 to 2. That inverse map is also a set permutation of this set. So the inverse map must also be represented somewhere within the group basically by a symbol. Indeed, hopefully you'll have realised that that inverse set permutation is exactly sigma squared here. Okay, so that means that when you compose sigma and sigma squared, it overall takes you back to the identity permutation, and therefore when you compose these two symbols together in the composition law, it will take you on to the identity symbol. Okay, so that is going to mean that we will have inverse elements within our group basically, okay, because the inverse of any set permutation is another set permutation and will be represented within the group basically. Okay, so this does form a group. Right, it doesn't form an abelian group, okay. Some of the entries here are not the same when you reflect them in diagonal lines. So basically, if you do tau 1, 2 composed with tau 1, 3, we get sigma squared, but if you compare that to what tau 1, 3 composed with tau 1, 2 is, you'll find that the answer to that is actually different. Okay, the answer to that is actually sigma, not sigma squared. Okay, so it's not abelian basically, it's not commutative. Right, so there's our S3 group. Okay, we now want to think about looking at subgroups of S3. Well, of course, there is the trivial subgroup, so the entire group is a subgroup, and of course there's also the subgroup where you just have the identity element on its own in a set. But we're looking to find some more interesting subgroups than that. Okay, so let's now think about some more interesting subgroups of S3. So one interesting subgroup that you can produce of S3 is where you put the identity element with the other two cyclic permutations, sigma and sigma squared, together. Okay, and that is just going to form the cyclic group of free elements, because in previous videos we've looked at the finite cyclic groups. Okay, and we've seen that the way that you build the finite cyclic groups is, again, you look at set permutations of sets containing, for instance, free elements. So if you want to create the cyclic group of free elements, you will look at set permutations of the set of free elements, but you won't look at all set permutations of the set of free elements. Okay, you'll only look at the cyclic permutations, which are the identity here, sigma and sigma squared. These are the permutations where you move every element along by a certain amount. Okay, so the identity element is the one where you move everything along by 0. Sigma is the element where you move everything along by 1. Sigma squared is then the element where you move everything along by 2. If you move everything along by 3, then it's just the identity back again. Okay, now, my claim is that if I put those free elements then in a subset, and I don't know how to do this because we need more paper, but then we lose our picture, which gives us all the insight. Okay, so what I'm going to do is I'm going to construct this subgroup, which is actually going to be C3, the cyclic group of free elements, and I'm just going to put the identity, sigma, and sigma squared together. So here's a subset of S3. So this is indeed a subset of S3. We've lost all three transpositions, but we've got those free elements there. Okay, now, my claim is that this is a group on its own, and hopefully you'll acknowledge that from the fact that C3, we know that that is a group. But let me just go over why this is a group, just to put the argument there. Okay, so why does this obey the axioms of group theory? Okay, so we will steal the composition from S3, but we need to make sure that we understand why that composition on this set of free elements obeys the axioms of group theory. So firstly, let's think about closure. Why does it obey closure? Okay, why is it the case that when you compose any two of these cyclic permutations together that you will end up with another cyclic permutation? Well, let's just do this with words. Okay, all of these cyclic permutations relate to moving every element along by a certain amount. If you compose two permutations together that move every element along by a certain amount, okay, if you compose two instructions like move it along by this amount and then move it along by this amount, you're still going to get a net instruction which tells you to move every element along by a certain amount. Okay, how could you not? If you move everything along by a certain amount and then move everything along by another amount, how can you not end up with a net instruction which is still just move everything along by a certain amount? Okay, so basically when you compose these cyclic permutations together, you're never going to end up with one of these transposition set permutations. You're always going to end up with another cyclic permutation, which is one of these instructions of the form move everything along by a certain amount. Okay, so that's why it obeys closure. We know that it will just obey associativity because it came from the larger group, so we don't need ever to worry about associativity. It contains the identity element, excellent, so we'll have an identity within our subgroup, and it contains inverses because sigma and sigma squared, we know, are each other's inverse. Sigma's inverse is sigma squared, and sigma squared's inverse is sigma. Okay, so we have inverses, and of course the identity is just its own inverse. Right, so that is a nice subgroup then of S3 basically, and indeed it is C3, the group that we have seen previously. Okay, however, there are other subgroups of S3 as well, and these are subgroups where you put the identity element into the set, and you also put one of the transpositions. So let me show you these other subgroups. So another example of a subgroup, Okay, and I'll just make sure this is straight. Okay, so another example of a subgroup of S3 is the set containing the identity and one of the transpositions, so choose whichever one you like. I will choose tau1,2, but you could have chosen tau1,3 or tau2,3. In fact, all of those three subsets are subgroups. Okay, I will just illustrate it for one of them, and I hope it will be obvious by our study of just one of them that the same applies for the other two, basically, where you choose the other two transpositions to put in there. Okay, so again, this is certainly a nice subset of S3. Okay, it's a smaller subset than the one that we've seen previously. Okay, and now what we just need to do is think about why this forms a group structure when we nick the transposition from S3, basically. So I might even actually draw out the transposition law for this one because it's so simple when we've only got two elements like so. So we have the two elements, the identity and tau1,2. So I'll give each of them a column and each of them a row like so. So the identity composed with the identity is obviously just the identity, okay? Because when you compose the identity set permutation with itself, you end up with the identity set permutation, okay? The identity composed with tau1,2 means do tau1,2 and then do the identity. So swap over 1 and 2 and then just map everything onto itself. That overall gives you net tau1,2. Okay, tau1,2 composed with the identity, again, that is just tau1,2. Okay, this is just because whenever you compose the identity permutation with any other permutation, it just overall gives you that other permutation back again. Now, what is tau1,2 composed with tau1,2? Well, this means swap 1 and 2 around, and then swap 1 and 2 around again, and then you do nothing to 3 in either of those cases, so that overall ends up being the identity back again. Okay, right, so that is certainly closed under composition, okay? All of the answers here are elements in capital H again, okay? And I hope you can appreciate that if I'd done this for tau1,3 or tau2,3, the composition table would look very, very similar, and again it would be closed, okay? Associativity we have from the larger group structure. We have an identity in here. Here is our identity, I, okay? And we also have inverses because tau1,2 is its own inverse. So it does obey the axioms of group theory, basically. And hopefully you will see that this is actually a group that is isomorphic to the symmetric group of two elements. Okay, if I just relabeled that as tau rather than tau1,2, then I could turn this composition table into my more normal composition table when I'm talking about S2, as we have done in previous videos. Okay, so that group is actually isomorphic to S2. It's capturing the exact same algebraic structure, just with different symbols. Indeed, I've given tau this subscript 1, 2, but that's all I've changed fundamentally. Okay, right. So that is also a subgroup of S3, basically. Okay, and indeed, as I say, you could also construct the subgroup which consists of the identity and tau1,3. Okay, and you could also construct the subgroup which consists of the identity and tau2,3, and all you'd have to do is turn this from being 1, 2 to being either 1, 3 or 2, 3. Okay, so just relabeled up all the entries here, and the composition table will be exactly the same. So all of these three subgroups here are actually isomorphic to one another. Okay, and they're all isomorphic to S2. Okay, right. So those four subgroups that we've just been looking at, the C3 one here, and then these three isomorphic subgroups which all consist of just the identity element with a single transposition. These are actually all of the subgroups of S3 that are proper subgroups. Okay, the total number of subgroups of S3 is 6, because you have S3 itself and the identity subgroup, which just consists of the identity. So you have the two trivial subgroups as well, plus these four proper subgroups that we've just been studying, giving us a total of 6 subgroups of S3. Okay, right, so that's some examples of subgroups then. In the next video, what we'll do is we'll do the subgroups of the integers under addition. So we'll look at another example, which is the group of integers under addition, and we'll have a look at the subgroups of that group.